Hello, welcome to our third lesson. This week we're going to cover two sections. First, we'll talk about the differences between linear and non-linear equations, and then we will study autonomous equations, and we'll use autonomous equations to talk about population dynamics. Starting with a theorem for linear equations. First of all, let's just be careful. Let's suppose we have two continuous functions, continuous on an open interval. Let's suppose we have our initial time, t0, inside this interval, and let's suppose y0 is just any number. Then the theorem says two things. It says that this initial value problem has a solution, and it says that this solution is unique. It says that the solution exists on this open interval, and it tells us that the solution is unique on this open interval. In other words, anytime we have a linear equation, as long as the functions p and g are continuous, we know that we have a unique solution. The theorem says that as long as p and g are continuous, the solution keeps existing. Or if we say this another way, the solution can only stop existing at a point where either p or g has a discontinuity. For non-linear equations, we also have a theorem, but the theorem is not as nice. Again, we start with our conditions. Now let's suppose that f is continuous on a rectangle. By rectangle, I mean t is between alpha and beta, and y is between gamma and delta c. And let's suppose that the y partial derivative of f is also continuous on this rectangle. Let's suppose the initial time and the initial value y0 in this rectangle. You can imagine a picture like this. Let's suppose we have a blue rectangle. Let's suppose that f and df dy are continuous on this rectangle, and the point t0, y0 is somewhere inside the rectangle. Then the theorem says, in some small interval inside the open interval from alpha to beta, there exists a unique solution to a non-linear initial value problem. What does this mean? This means that a little bit of solution exists and is unique. It doesn't tell us how big our solution is. All it tells us is that this little bit of the solution exists. Maybe the solution exists on the whole rectangle. We don't know that. Maybe the solution exists outside of the rectangle. Okay. Again, we don't know this. All we know from the theorem is there's a very small piece of solution which exists. But this does tell us that two solutions to a first order equation cannot intersect. Either a linear equation or a non-linear equation. It's not possible to have two solutions which intersect. It's possible to have two solutions which become very close to each other. That's okay. But it's not possible to have two solutions which cross each other. That's not possible. To understand why, let's suppose we did have two solutions which intersected, two solutions which crossed, and let's suppose they intersect at the point t0, y0. Then that means we have two solutions to the initial value problem that I've written. But the theorem says this is not possible. The theorem says there is a unique solution. to this initial value problem. So therefore, two solutions to first order equations cannot intersect, with the caveat that as long as f is continuous on our rectangle, as long as df dy is continuous on the rectangle. In other words, as long as f is some nice function, it's not possible for two solutions to intersect. That's all I want to say about the differences between first order and second order equations. If you have the book by Boyce and DePrima, you see they have a large section here. They give lots of details, but I think that's not necessary for us. For us, it's just necessary to understand solutions exist and you are unique and do not intersect. For the rest of today's class, we're going to be talking about autonomous equations. What is an autonomous equation? An autonomous equation is an equation of the form dy dt is equal to some function of y. Usually we have functions of both t and y. If our function doesn't depend on t, if it's only a function of y, then our equation is called autonomous. Now, you may immediately note that every autonomous equation is a separable equation, because of course we could rearrange this to dy over f of y is equal to dt. So already you know how to solve autonomous equations, but we're not interested in that in this section. We're interested in what can we learn about solutions to the equations like this without having to solve the equation. For the first example, I want to talk about cats. Let yt be the number of cats in Istanbul. We want to model the number of cats in Istanbul, and the simplest model would be to assume that the rate of change of y is proportional to y. In other words, the simplest model is a model where we assume that dy dt is equal to some constant r multiplied by y. And we're going to be assuming that r is a positive constant. We know how to solve this initial value problem. This is a very simple problem. We know that the solution is y0 e to the power rt. So we know that the graph of the solution looks like this. What does this tell us? This is good for small y, but the model predicts that the number of cats in Istanbul will increase exponentially for all time. There will be 1,000 cats and 1,000,000 cats, 10 million cats, 1,000,000,000 cats, 1,000,000,000,000 cats, quadrillion cats, etc., etc., a Google of cats. And we know that this is not true. It's not possible for the number of cats in Istanbul to just keep increasing to incredibly high numbers. At some point, the food will run out, or there'll be no space for more cats, or people in Istanbul will become angry with the cats, start killing them. We know that this model cannot be correct. So we're going to need a better model. To make our model a little bit more sophisticated, instead of a constant r, let's suppose we replace this by some function h of y. Now remember, we said the previous model was good if y is small. So if y is small, I'm happy for h of y to be the same as r. The problem happens when r gets bigger and bigger. I want h of y to decrease as y grows larger, and in fact I want h of y to be negative for large y. The simplest such function would be h of y is equal to r minus ay. If y is very small, then h of y is approximately equal to r. As y gets bigger, h gets smaller. we have a graph which looks something like this. So our differential equation becomes dy dt is equal to r minus ay multiplied by y. Or we can divide by a and write this as r multiplied by 1 minus y over k y, where k is a new constant equal to r divided by a. This equation, boxed in orange, is called the logistic equation. I don't want to solve this equation. I want to try to understand this equation just by looking at it. The first thing to do is to look for equilibrium solutions or constant solutions. These are solutions where dy dt is equal to 0 for all t. How can we find equilibrium solutions? We can start by saying we want dy dt equal to 0. In other words, we want r 1 minus y over ky to be equal to 0. R, we said, was strictly positive, so this must imply that either y is 0 or y is equal to k. These equilibrium solutions are important. I'm going to show you some solutions to the logistic equation, and you see that all of the other solutions either converge to one of the equilibrium solutions or they diverge from the other one. Each of these curves is a solution to the logistic equation. You see they converge towards y is equal to k, and the bottom ones at least diverge from y equal to 0. To understand this behavior, to understand how we can draw these solutions without having to solve the equation, what we do is we graph dy dt against y. I can write it here. Remember, dy dt was r 1 minus y over k multiplied by y. So we're graphing this function against y. This axis is the y-axis. This axis is dy dt. And we get a curve like this. As we said, the curve is equal to 0 when y is equal to 0, y is equal to k. What can we note from this graph? We can note that because if dy dt is strictly greater than 0, y is increasing, and because if dy dt is negative, that means y is decreasing. Y must be increasing between 0 and k. Y must be decreasing if y is greater than k. We can show this on the picture by drawing green arrows. When dy dt is positive, or when y is increasing, we draw a green arrow to the right. When dy dt is negative, which means that y is decreasing, we draw a green arrow to the left. To investigate further, we can look at the second derivative of y. If dy dt is f of y, then d squared y dt squared must be the derivative of f of y of t. By the chain rule, this is f prime of y dy dt, but dy dt is just f of y, so we get f prime of y, f of y. We know that the solution will be concave up, either the left curve or the right curve, when the second derivative is strictly positive. How do we get the second derivative strictly positive? We must have either f prime and f are both positive, or f prime and f must be both negative. And the solution will be concave down, curve like this, or curve like this. This happens when the second derivative of y is strictly negative. How can we make the second derivative strictly negative? From f prime and f, we need one of them to be positive and we need one of them to be negative. Let's go back to the graph of f of y against y, or r 1 minus y over ky against y. We can see that if y is between 0 and k over 2, so just the first part of the graph, f is positive, and f prime is positive because the graph is sloping upwards. So we have f positive multiplied by f positive, positive multiplied by positive is positive. We have increasing and concave up. Let's look at the next part now, the middle part of the graph. In the middle part of the graph, f is positive, but now f is going down, so f prime is negative. Positive multiplied by negative is negative, which means concave down. Here, y must be increasing and concave down. And then finally, we can look at the right part of the graph. F is negative and f prime is negative. That means y is decreasing. Negative multiplied by negative is positive. So we must be concave up. There's a mistake here. There's a mistake here. Moreover, remember that a theorem from today told us that two solutions do not intersect. We talked about this earlier. This is enough information to draw solutions. Let's look at the bottom part first of all. Just look at y between 0 and k over 2. We said the graph should be increasing and concave up. So we can draw some curves which are increasing and concave up. Then let's look at the middle part. Curves should be increasing and concave down. Any graph we draw here should be increasing and concave down. Remember, they can't intersect, so they can get close together, but they don't cross each other. And then finally, in the top part of the graph, the curve should be decreasing but concave up. So we draw some curves which are decreasing and concave up, making sure that the graphs don't intersect. Without solving the equation, we can learn enough that we can sketch some solutions. We can understand the behavior of the solutions without actually finding a formula for the solutions. Because the solutions converge to the equilibrium solution y is equal to k, we say that y equal to k is an asymptotically stable equilibrium solution, or another way to say the same thing, an asymptotically stable critical point. Because the solutions diverge from y equal to 0, we say that y equal to 0 is an unstable equilibrium solution, or an unstable critical point. To understand this idea, let's imagine we have some pendulum. Suppose we have something like this. So suppose it's attached just here, and it's allowed to swing. What positions could we put the pendulum in such that it wouldn't move? We could have the pendulum hanging straight downwards, or we could have our pendulum vertically up if we balanced it just right. There would be two equilibrium solutions to the position of the pendulum. And what happens if we just push the pendulum just a little bit? Let's suppose I push this pendulum just a very small amount. What happens? It would just return to its existing position, because this would be a stable position. What about the pendulum which is vertically upwards, just balanced in position? What happens if I just push this pendulum a very small amount? What happens is that the pendulum would move a lot. It would swing all of the way down, because this position of the pendulum is an unstable position. We can understand stability using the green arrows which I introduced earlier. If all of the green arrows are moving towards the equilibrium solution, three possibilities. If we have two green arrows, one on the left, one on the right, they're both going towards it. If we are at the end point of our domain, we would only have one green arrow on the left or one green arrow on the right, pointing towards the equilibrium solution. If we have any pictures like this, the equilibrium solution is asymptotically stable. If all of the green arrows are moving away, then the equilibrium solution must be unstable. And if we have a mixture of arrows going towards or going away, we say that the equilibrium solution is semi-stable. For example, find all of the critical points of dy dt is equal to y, 1 minus y squared, where we're saying that y0 can be any number between minus infinity and infinity. And then classify each critical point or each equilibrium solution as asymptotically stable, unstable, or semi-stable. The first thing to do is to draw the graph of f against y. Here our function f of y is y, 1 minus y squared. We draw the graph of this function against y. And then we add our green arrows. Where the function is positive, the arrow points to the right. When the function is negative, the arrow points to the left. Here the function is positive, so we draw a green arrow pointing to the right. Here the function is negative, so we draw a green arrow pointing to the left. That's enough information to answer this question. Where are the equilibrium solutions? Here, here, and here. The equilibrium solutions are -1, 0, and 1. Are they asymptotically stable, unstable, or semi-stable? We look at the green arrows. At -1, both of the arrows are pointing towards it, so it's asymptotically stable. At 0, both of the arrows are moving away, so it's unstable. And at 1, both of the arrows are moving towards, so the critical point or the equilibrium solution must be asymptotically stable. Another example. Find all of the critical points of y minus 2 squared. Again, y0 is between minus infinity and infinity. And classify each as asymptotically stable, unstable, or semi-stable. First thing to do is to plot this graph. Because we're going between minus infinity and infinity, our y-axis must go from minus infinity to infinity. How can we get 0 here? Y could be 0, or y could be 2. These are our critical points. How can we quickly and easily sketch the graph? We can just calculate this graph at a few points. Let's suppose y is equal to 1. Then what do we have? We have 1 multiplied by 1 minus 2, which is minus 1 squared, or 1 multiplied by 1, which is a positive number. So this part of the graph must be positive. What about instead we look at, say, y is equal to 3. 3 multiplied by 3 minus 2 squared. 3 multiplied by 1 is again positive. This part of the graph must be positive. I'll just connect this up in some neat way. And then finally, we need to see what's happening on the left. Let's say y is minus 1. Minus 1 multiplied by minus 1 minus 2, or minus 3 squared is plus 9. Minus 1 multiplied by plus 9 is a negative number. So the left part of the graph must go down like this. And that's enough. We don't need a perfect graph. We just need to know where is it positive, where is it negative. And then we can draw our green arrows. On the left of the graph is negative, so green arrow to the left, green arrow to the right because the graph is positive, and again, green arrow to the right. Let's make this a little bit neater. Here we are. Using a computer, this is the graph of this function. The critical points are 0 and 2. Y equal to 0 is unstable because both arrows move away. At 2, one of the arrows is moving towards it, one of the arrows is pointing away. So y equal to 2 is semi-stable. Now let's go back to talking about the number of cats in Istanbul. Now I want to introduce a different model, a model with a critical threshold. Now let's consider dy dt is equal to minus r, 1 minus y over t multiplied by y, where capital T and r are positive constants. We can plot f of y against y, as we were doing before. This axis is the y-axis. This axis is the f of y axis, where f of y is this function. And we draw our green arrows. We can see we have two equilibrium solutions, 0 and t. We can see that 0 is asymptotically stable because the only arrow points towards it. T must be unstable because both arrows are pointing away. Using this information, we can sketch some solutions. Draw the axis like this. Y is the number of cats. We can't have a negative number of cats, so we're only drawing the positive y-axis, and I'm only interested in positive time. We have y equal to 0, so we have an equilibrium solution here, and we have y equal to t. This. And if I copy the green arrows, this one's going down, this one was going up. I can sketch some solutions. Let's suppose I start just here at this blue spot. The green arrow says the solution goes upwards, so I can quickly draw it. Suppose I start just here, green arrow says go upwards. Draw a solution, go upwards, and so on. Let's suppose I start at this point. The green arrow is pointing downwards, our solution should decrease. It can't cross over 0 because two solutions can't intersect, but you can get close to it. We go down and we get close to it. The solution should look something like this. And we carry on. We can just keep sketching some solutions because we know roughly what they will look like. Very quickly, we can sketch some solutions to this equation, and then that can give us information to understand the equation. I can draw this with a computer to make this neater. Here we go. Depending on the initial condition y0, assuming y0 is not t, we either have the y tends to 0 or y tends to infinity. This number t is called a threshold level. Below this level, no growth happens. The population of some species have this threshold property. If there are not enough individuals of the species to breed, then the species becomes extinct. But again, like the first model, this model predicts that the number of cats in Istanbul will increase to infinity. And we don't want this, we want a more advanced model. So next example. Let's combine the last two models for the number of cats, the logistic equation and the equation with a threshold, to get logistic growth with a threshold. We have the threshold term, 1 minus y over t. We have our logistic growth term, which stops the number of cats from going to infinity. That's 1 minus y over k. We have our y on the end. We have our constant r. And just to make everything work, and I'll leave this for you to think about, we put a minus sign in it, just so that the behavior is right. Now, on this model, we require that capital K and capital T are positive constants, and that capital K is bigger than capital T. And again, I want small r to be a positive constant. Here is the graph of f of y against y, or y prime against y. And I've drawn the green arrows as before. We have three equilibrium solutions, 0, t, and k. Y equal to 0 is asymptotically stable, y equal to t is unstable, y is equal to k is asymptotically stable. And solutions look like this. Just with the information on the previous slides, you could now sketch the solutions. This is an equation which actually has been used by biologists to model the populations of some animals. Some animals have K, an ideal population size. If there's too many animals, there's not enough food, the number decreases. If the number of animals is a little bit less than K, then the animals will breed and that number will increase to K. They also can have the threshold property where if there's not enough of the animal in an area, they can't breed, the animal goes extinct in that area or in the world. And perhaps I've talked too quickly, or I didn't put enough material in this week. That's all I've prepared for this week. Next week, we are going to talk about exact equations and substitutions.